Welcome to Interaction Between Climate and the Biosphere, Chapter 7 from your textbook, talking about the connections between wind, climate, and biomes, because you see, everything we do affects some other part of the biosphere. There are no boundaries. There are no artificial boundaries going to protect our air from air that has been traveling over from China. There's a lot of pollution on the West Coast. That 10% of the smog in California actually comes from China. You see, wind is an indirect form of solar energy. It helps moderate the Earth's climate, and it helps to circulate heat, moisture, plant nutrients, soil, and unfortunately also air pollution. And the tropics would not be livable because it'd be so hot, and the rest of the planet would be too cold without wind. And wind is circulating, like I said, heat, moisture, plant nutrients, soil particles, and unfortunately long-lived air pollutants as well. Some plant nutrients, though, have been helpful because they have traveled from the Sahara Desert over to areas in the Caribbean. And what's been nice as well is that some of the particles from the soil particles have also helped to build soil in other parts of the world. And soil particles, they say, from Africa ended up blocking out some of the sun, which helped decrease the intensity of some of the hurricanes during hurricane season because it blocked the sun from heating up the water, which would have increased the energy going toward those hurricanes and those storms. The bad part, though, is that we also have long-lived air pollutants. And like I said, 10% of the smog on the west coast of California is from China. Other problems too is it impacts globally. It impacts like the fungus and rust from one area can impact another part of the world. Your book tells us that there are pesticides that have been banned in the United States, but they're being blown over from Africa, and it's impacting the coral reefs, and it's impacting some of the farmland in Florida. And then there's fungus that might be degrading the coral reefs around the Florida Keys and Caribbean. Another big problem, though, is that the iron-rich dust from Africa will increase the productivity of algae, and this particular protist can, when it increase the quantity of it, you have something called an algal bloom, and there's certain shellfish that are filter feeders, so they'll eat the algae, and then when humans eat the shellfish, the large quantity of that particular protist will make you sick, and it's actually toxic. It can kill you. Some of the protists actually, when you have algal blooms, it's because it will kill the fish because of a mechanical hook that kind of hooks into the fish. But other types of protists, when you eat them, it's actually a toxin that's released and ingested. And even in small quantities, it can be harmful. But when you have an algal bloom, that means you're going to have like a red tide. It's going to have an even larger impact on your health. Dust blown from West Africa to the Amazonian rainforest. So they say this has actually been helpful because it's been giving the rainforest some more nutrients. Their soil is already known for being nutrient poor. There is a link between air circulation, ocean currents, and biomes. So from the previous lecture, remember, air circulation in the lower atmosphere, so in other words in the troposphere, is due to uneven heating of the Earth's surface by the sun. So the differences in solar intensity at the uneven heating of the Earth's surface by the sun. Solar intensity at the equator is greater than the solar intensity at the poles because you have the same amount of light, but it's spread out a larger area. The rotation of the Earth on its axis and the properties of air, water, and land. So when basically almost you want to say the properties of matter in general. What happens to any piece of matter when it is heated? It's going to expand and become less dense. What happens when it's cooled? It's going to contract and become more dense. Then we have currents. Currents are caused by prevailing winds, the Earth's rotation, and redistribution of heat from the sun. Okay, this is an example of a convection cell. The title says energy transfer by convection in the atmosphere. So again, the properties of matter that we were just talking about, we'll start over here. Basically, when this heats up, it's going to expand. And you've got, whoa, sorry, it's been going crazy. Okay, there. The water, the air is going to heat up. Here you go. And then as it heats up, it's taking basically this current right here is pulling moisture off of the ocean right here. And when it pulls the moisture and it goes up, it's heating up. So therefore it's going to rise and expand. And as that happens, it is going to cool. And it's when it cools, it's going to condense, and remember the properties of gravity say it's going to now fall as precipitation. So that air pocket's going to continue on though. It's going to keep on going over here. But now you have cool, dry air because you lost all the moisture over here. So this area right here is going to have a lot of rainfall. So it started out, you just have this air mass that's, kind of building up moisture, and it's going to drop the moisture here. And so if you want to think about it, since it's rising up, then you want to think about that as low pressure. You don't have something pushing down on you. So when you hear the meteorologists talk about low pressure, it's because the air mass is going up, away from you, off of you. And so that happens when the air is hot. So if you want to think low pressure is hot, and it's going to cool. Let me find my cursor. There it is. When it cools over here, well then once it's cooling, it will compress, and then it's going to warm up. And then as it warms right here, you're going to get this air mass that is warm and dry. Okay, so it's warm, dry air, but a lot of times it's cool as well. So just know it's dry, and then you're going to have high pressure when it's coming down on you. Anytime you have a mass of air going down, that's going to be high pressure. And it kind of happens over and over again. So basically what happens is you have 3 convection cells north of the equator, and you have 3 convection cells south of the equator. And the way I always think about this is what happens at the equator here, you have your tropics and your tropical rainforests right here, because remember, warm air, and it's going to drop the moisture. And then at 30 degrees latitude, both directions, so if I were going north, this is 30 degrees north, you are going to have a dry, warm mass. So in other words, you are going to have a desert. And the same thing happens at 30 degrees south, except for your convection is going to go this direction. Go this way. I wish I could make my little marker work down here, but I can't. Okay, so here's another example of what I was just telling you. So if we start with our convection cell starting at the equator right here, it's always easy to remember it because here, this is your tropics, your tropical rainforest. You're going to have your low pressure. It's going to rise up, and then as the molecule cools off, it will drop the moisture there. Well, your air cell is going to continue flowing. Remember, we have patterns going on with the uneven heating of the sun. We're rotating on our axis, so you're going to have this continuation of the convection cell. So when you have your desert. Well, it kind of ends up being opposite. So same thing at 6 degrees latitude. Both again, you're going to rise up, and you're going to have low pressure, and it's going to drop the moisture. And then as you come, where are you, cursor? Poop. Okay, here you go. You're going to have your dry air again. So theoretically, your your poles would be deserts. Okay, now Arctic tundra, yes, and if you go to 0 degrees, there's not a landmass at that spot. But anyway, if it was, it would be desert. So Arctic tundra is like a frozen desert, if you will. And then Antarctica, also a frozen desert down here. So see, 30 degrees south, same thing happens. So you're going to use this picture tomorrow when y'all come in to do an activity. But you should be able to predict based on the latitude what biome you're going to see. Obviously, there are some the topography is going to play a part of that as well, whether or not you have a microclimate and whether or not you have a city built in a particular spot, or if you have a mountain range there. So there's other factors, but for the most part, this is kind of what you would see at the different biomes. Okay, let's see. Global air circulation here. So basically, since we have the solar energy hitting at this spot right here at 0 degrees latitude, what this is showing you right here is that the largest input of the solar energy is going to be at 0 degrees. Obviously, that's the equator. But as the air heats, it rises and moves toward the poles, which would be no problem. But the Earth is rotating. So since the Earth is rotating, you see a pattern that the convection cells will go on. So like I was telling one of the classes, when you're naming your trade winds, it starts when you're using these pictures. I always think of it as it's named after the starting point. So where's my cursor? So for northeast trades, notice that it starts northeast and moves southwest. So we call that a northeast trade wind right there. And same thing here, southeast trade wind. These are very strong winds because remember how I told you at the equator, it's going to be the wind speed will be faster because it rotates faster at the equator than it does the pole. And so these are going to be very strong winds. And so if this actually impacts the sea level in certain areas. So that's an important fact. Remember that for a couple slides down. I'm going to tell you why that's so important right down here, especially at, where's my cursor? Especially right here off the coast of Peru. Something very significant happens over here because this current here is so strong. These prevailing winds are so strong right there. Okay, so here's an interaction of convection cells, prevailing winds, and ocean currents. You see, the ocean also plays a part in our convection cells in our wind pattern because it absorbs heat, and so when it absorbs heat, that's how it's also redistributing, like I said on that first slide, how it's redistributing the heat from the sun because ocean is absorbing so much of it. And so here you can see, this one's kind of busy, but you can see on the outside edge, you can see the different convection cells. These are the ones on the outside. I want you to remember that the ones closest to the equator, as you leave the equator, these are called Hadley cells. You're going to have to know that. So this is a Hadley cell, this is a Hadley cell. And then this big one right here, this is called a Ferrel cell. And this one down here is also called a Ferrel cell. And then the cells closest to the poles are your polar cells. Okay, so polar, Ferrel, Hadley, Hadley, Ferrel, polar. And then notice the your trade winds, that if you want to draw these on a map, which you're going to do tomorrow, your trade winds are going to, actually I say that's on Friday, that is. Your trade winds look like they're going toward the west, but then they're going to alternate. So then the next ones are going to go, your next ones are going to go to the right, and then your polars are going to go back down to the left again. So they're just kind of every other, if that's one way to remember it. I usually, when I'm starting my drawings to remember these, I always start at the equator and work my way out because there is a pattern to it. Okay, here's a little animation for air circulation. Let's try this together. Yes. Okay, we are going to try to see if we can figure out what direction these cells are going. And the direction that they are going, remember, low pressure, and if it's coming down, it's going to be high pressure. So where do we know that we have low pressure? Right here at the equator, right? So we want to make sure the air is going away from us at the equator. So that one's got to go away from us at the equator, and this one's going away from us at the equator. Okay, and that's low pressure right there, which means it's going to have rainfall fall right there. Okay, so the next one, I always kind of think of it as opposite. So if that one's going there, that one must go there. And that one must go there. And so this one is going, we already hit that one, didn't I? There. There. Y'all are doing a great job with this. Where does this one go? Yes, good job. Okay, so since we know that the equator is low pressure, what symbol should we put? Is it going to be rainy there, or is it going to be dry? Yeah, you're going to have a cloud because it's raining, because it's low pressure. What's going to happen at 30 degrees north and 30 degrees south of the equator? You're right, high pressure and sometimes cool, but if you're down here, it's going to be warm air mass. Regardless, it's dry. We're going to have dry there, and we're going to have dry there. And then what happens at 60 degrees? Because remember, your convection cell, let's see, at 60, it's going away from us, so therefore it must be low pressure. You have air masses moving off of you. Yes, so that means it's going to be it could be, some people call it temperate, some people call it, regardless, you're going to have high amounts of rainfall. Yay! Excellent job. Okay. What's next? Okay, this is another really cool figure because it shows you the relationship of climate, between climate and ocean currents. Because you gotta remember, the properties of matter, we said when things are heated, when matter is heated, it expands. And when something expands, the density, which is just a measure of mass over volume, your mass is going to stay the same, but your volume increases. Therefore, your density will, as it expands, your density is going to decrease. It's an inverse relationship. So at the equator, the sea level is actually a little bit higher than at your poles because the water is hotter here. So that kind of gives us a natural slope. So that one property of matter also helps drive the currents. But what's really cool about the currents is that they are all connected. It's like a convection belt, and where the dense, nutrient-rich cold water is flowing underneath the less dense, warm, shallow waters. So let's see what you can see on this animation. Yes, yeah. Okay, start. It tells you here. Ooh, in which hemisphere are the currents going in a counterclockwise direction? Good job. Okay. And the last thing I wanted to talk to you about real quickly is what happens when, for whatever reason, we lose those very, very, very strong trade winds I was telling you about. So it's very significant at the equatorial Pacific Ocean. This right here is an example of your equatorial Pacific Ocean. So what normally happens here is these trade winds are so strong that the sea level is actually higher over in New Zealand and Australia, off the east coast of Australia. And by doing that, you get something called a thermocline. It's going to be this direction. I'll show you in class. I'll do another little graphic of it. Oh wait, is that up here? Normal conditions. This kind of tells you also that we have such strong trade winds up here that you get an upwelling. This blue is going to represent the upwelling. You get this nutrient-rich cold water that is going to push up off the coast of Peru over here. This is South America right there. So over here, you can see it again. A strong current is going to pull up this cold water because the top of it is so sloshed to the left that the bottom of it is able to upwell. And when I say upwelling, this is where the bottom of the ocean is where all the detritus falls, all the dead, decayed organisms are going to fall down there, just a lot of nutrients. And so that nutrient-rich water comes up to the edge of South America over here, but in particular Peru. And this is awesome for their fish, and this really impacts their economy right there. Well, what happens in an El Nino year, I didn't put a title on this. Let's talk about El Nino. In El Nino, for whatever reason, these trade winds decrease, which means the current of the ocean decreases, which means like all this water is going to slosh back over to the west coast of Peru. You can see it right here. So now the water is going to slosh back. What do you see that we're missing down here that we have up here? Yes, that nutrient-rich cold water is no longer there. So I'll show you a thermocline in class, but our thermocline is now more even instead of diagonal over here. And basically that means that we are losing all that nutrient-rich water. That means the fish die over here. There are some other really significant global impacts during an El Nino year. So some little facts about El Nino up here. Occurs every 3 to 7 years. They can last weeks or they can last years. You have cooler, wetter conditions in southeast United States. Cooler, wetter conditions. Can y'all think of a time when perhaps your basement might have flooded sometime in the last few years? Remember 2009, we had extreme weather conditions. Remember that the Olympics in Canada, they had to bring in snow for the Olympics because you have dry weather in southern Africa, Southeast Asia, and Indonesia, and Australia. You not actually get a lot of forest fires in Australia and Africa. A lot of fires are started. But look here, warm weather in Alaska, Canada, and northern U.S. So I think it was 2010 in Calgary, the Olympic Games, they had to bring in snow to Canada because it was an El Nino year. That was coming right off of our huge, massive flood where I think even the basement here at Brookwood down the dungeon got flooded. So it has a global impact, very significant. Thanks for listening.